Dear learners, greetings from IIT Guwahati. I welcome you for this course Computational Gas Dynamics. So, this course is split into 4 weeks. In the first part of this lecture, that is in the week 1, we will cover review of thermodynamics and fluid mechanics, which are in particular relevant for this course gas dynamics. Now, in this lecture, we have 2 videos. In the first video, I will touch upon the fluid mechanics aspects, and in the second video, you will be learning about the thermodynamic aspects. And ultimately, at the end of the lecture, we will try to evaluate with some relevant problems which are which pertains to this lecture. Since it is a review of fluid mechanics and gas dynamics mainly deals with the knowledge of fluid mechanics and thermodynamics. So, it is very essential that you should know about the fundamental aspects of fluid mechanics, and most of these contents are already known to you in the basic UG syllabus. So, in my video, I will just touch upon some important topics, some important terms which are associated in the fluid mechanics course. So, normally the state of the matter is defined in 3 states. One is solid, liquid and gas. So, the essential characteristics of solid is that they can resist the applied shear by deforming, which is not true for fluid, because fluids deform continuously as long as the force is being applied onto it. But in mathematical term, how do you distinguish this solid and fluid? For solids, we can say that shear stress is proportional to strain. So, that is stress strain relationship which is associated in terms of Young's modulus, but that is not relevant for our analysis, but because we are mainly dealing with fluids, and in fluids shear stress is proportional to the strain rate, and the strain rate is expressed in terms of du by dy, means change in the velocity with respect to change in the distance along that direction. Now, moving further is that when you talk about fluid essentially consists 2 parts, one is liquids, other is gas, and both have some common characteristics, but basic difference between these two is that liquids are generally incompressible, but gases bear dual characteristics, right? That is, in certain conditions gases behaves in an incompressible manner, in some cases gases behaves in a compressible manner. Because of their characteristics, we can compress the gas under a certain container to a pressure as much as we can, as long as the container resists that force. So, basically speaking, that in our course of gas dynamics, we will talk about the nature of the gas, which is very specific, and in terms of the fact that compressibility effect comes into pictures. So, based on these facts and certain conditions, one can say that the behavior and motion of the gases are treated separately, and they comes under the broad name of compressible flow. In fact, gas dynamics is another analogous term associated with compressible flows. So, the theory of gas dynamics describes the behavior of gas, and in this case in our course we will talk about gas as air, when the compressibility effect and temperature change becomes important. Now, coming back to further concepts, we can classify the fluid flow as inviscid and viscous flow, and viscous flows are quantified by the term called as viscosity, and in our case we will talk something of viscosity effect for the gases. Now, when I am talking about these classifications, we are mostly talking about these classifications which will be dealing mainly for gases which are compressible in nature. Now, the second category of fluid flow we can say internal flow, which is bounded by the surface. So, flow inside a duct, and external flow which is unbounded, flow over an airfoil. Third category is laminar and turbulent flow. The flow when it happens in a organized manner, we call this as laminar flow, and turbulent flow are characterized by disorder flow patterns. So, Reynolds number is the key parameter that decides nature of laminar or turbulent flow. Then we have steady and unsteady flows, they are time dependent and time independent. Then we have natural and forced flow, where buoyancy is the key factor, and in most of our cases we do not mainly deal with natural or forced flow. And most important, which is the very vital factor, is the incompressible and compressible flow. And when you deal with the compressible flow, we say that during the motion of the gas or air, the density change must happen due to two effects. One is pressure as well as temperature, and that pressure and temperature effect, if due to this temperature and pressure effect, if density changes are higher than 5%, then it is characterized as compressible flow, or compressibility effect takes the dominance. Then dimensionality of the flow field, that means one can think of dimensionality in terms of one dimensional, two dimensional and three dimensional. Now, our focus would be mainly these gas dynamics, which we will be talking about. They are mostly inviscid, compressible, naturally occurring laminar flows, and they are addressed through steady analysis in an orthogonal framework. So, this is the topic that the things that we are going to discuss in this course. Then moving further, we all know that the fundamental properties of the fluid. The main properties are pressure, temperature and density. In fact, density characterizes whether the flow is compressible or incompressible. And in addition to that, all types of addition to this, we also deal with some other type of properties. They are kinematic properties and transport properties. So, during the kinematic properties, when there is a fluid motions, we normally define velocity field, and for that velocity field is recognized through a displacement vector. So, when that motion occurs, then we have acceleration related to velocity, then we have angular velocity, then due to this velocity of the flow, we also deal with the volumetric change. So, all these terms we are going to be associated when you deal with the computational aspects of gas dynamics. Other properties of the fluids, they are like transport properties, and transport properties essentially means that movement of mass, momentum and heat for a fluid, and during the motion, if these properties gets transported, we call them as a transport properties. The transport properties are mainly viscosity, and that viscosity relates to momentum flux and to velocity gradient. Then we have thermal conductivity, that relates heat flux to temperature gradient. Then we have diffusion coefficient, that relates to mass transfer to the concentration gradient. But however, in our course we will try to see the effect of viscosity and thermal conductivity, how it affects when there is a pressure and temperature change. Now, to address these changes, what has been proposed in this gas dynamics course is that there is a term called as Sutherland's law for viscosity, and it has been seen that with a reasonable experimental validation that the thermal conductivity and viscosity, they are vital parameters and they are mostly dependent on the temperatures. So, during a fluid flow, if the temperature change is significant, then it is very likely that viscosity and thermal conductivity is going to change. So, now Sutherland's law addresses that how we can find out the variation of thermal conductivity and viscosity with respect to temperatures. So, what we have is that thermal conductivity and viscosity, they are taken at any arbitrary temperatures, and mu 0 and k 0 are viscosity and thermal conductivity for the gases at some reference temperature T 0. Now, once you have know these reference temperatures, these relations help us to evaluate thermal conductivity and viscosity at a particular temperatures. Now, next point that we are going to address, that in the gas dynamics course, as the fluid as a continuum, which means that when you take the behavior of the gas, we take its global properties, not microscopic properties. Now, the global behavior of these fluid properties is addressed when by considering the term which is called as Nunsen number. So, Nunsen number talks about the which is the ratio of lambda by L, and lambda stands as molecular mean free path and L stands as characteristics linear dimension in the flow field. Now, when the fluid is treated as a continuum, lambda and L, they are of same scale. That means, we are not interested in the microscopic approach or changes that is happening in the microscopic manner. So, for a continuum flow, the Nunsen number is much less than 0.01, and if it is higher than that, then other types of flow come into picture, that is slip flow and free molecular flow. Why we are addressing all these things? Because in certain gas dynamic environment, the flow can be treated as a continuum, flow can be treated as a slip flow or free molecular flow. When the temperatures and temperatures are very high, then such at very low temperature and pressure or high temperature and pressure, this flow field we can think about when there is not sufficient number of molecules. So, those are in a different types of environment called as rarefied gas dynamics. So, however, in our course we treat this fluid as a continuum. Now, moving to the fluid as a continuum, and we view the fluid in terms of the streamline, and the streamline pattern can be drawn at any in a flow field. In a flow field, there can be infinite number of streamlines. So, while as an observer you can look at the fluid element in two different aspects along the streamline. So, one case we can think that there is a small elemental volume dV which is fixed in the space and fluid is moving through it. The other aspect is that the same volume, the small volume dV is moving along the streamlines. So, at that any point when you draw a tangent, it gives its velocity and Mach number. So, that is what we say. So, here we talk about the global behavior of the streamline, and here you talk about the individual behavior of the streamline. So, based on that, we call them as a Lagrangian description or Eulerian descriptions. Now, in a Lagrangian descriptions, the motion is identified in which the fluid particle is studied through time, whereas in Eulerian descriptions, the attention is focused to fixed point in the space and variations are attached when the fluid particle passes through that point. So, in Lagrangian description is a system approach, Eulerian description is a control volume approach. So, these two things that means for a Lagrangian description one can represent the velocity of a particle. In an Eulerian description you can say velocity of the flow field. And there is a link between this Lagrangian and Eulerian descriptions that is related to a theorem called as Reynolds transport theorems that talks about the relation. It is a completely mathematical term. Any property which that varies with space and time, they can be mathematically related in through Eulerian and Lagrangian approach. So, these tools will be very useful when you talk about computational gas dynamics aspects. Then next point that we are going to discuss is the governing laws of fluid motions. So, normally gas dynamics, when you deal with it, is the aerodynamic aspects of flying objects. So, any aerodynamic body, it experiences lift and drag, that is forces that acts on the body. It also experiences movements and also heat transfer from the flow fields. Now, when it travels at high altitude, there is a the drag is less, that means at high altitude we will have a less pressure and less temperature, because of which the body can travel faster, but side by side it experiences drags, movements and heat transfer in the flow field. Now, to talk about these changes in the flow field in terms of pressure, temperature, density, velocity, then we frame some algebraical differential or integral equations. So, all these equations are summarized as continuity equations, which talks about conservation of mass. Momentum equation talks about Newton's laws of motions. Energy equation is the first law of thermodynamics. Entropy equation is the second law of thermodynamics. And we have also equation of state, which is a perfect gas equation assumption. So, these are the some of the governing laws of fluid motions when represented as in integral form. So, we have continuous equations, we have momentum equations, we have energy equations. So, these equations are necessary. Continuity equation talks about the mass, momentum equation talks about moments and forces, which is the net effect of resultant force, and energy equation talks about energy coming into the system and that is going out of the systems. So, this is nothing but auditing of mass, forces and energy, and they are represented in integral form. Now, in the similar logics, we can also frame the differential equations, and when you talk about differential equation, you talk about small elemental fluid element, and for that fluid element we derive the set of equations. So, here also same thing, we have continuity equation, momentum equation, energy equation, first law, and then we have entropy equations. All these equations are very vital while dealing with in this course. So, one of the summary that we can find out that if a flow is steady, the entropy remains constant along a streamline in an adiabatic inviscid flow, because in a case when in a particular when you talk about an adiabatic inviscid flow, entropy remains constant, and if the flow originates from a constant entropy reservoir such as free stream ahead of the body, this is essentially the case for the flying bodies. Each streamline will have same value of entropy. So, this is one of the important consequence for the analysis of compressible flow. So, in our study we will be using this entropy as one of the important tool for analysis of compressible flow. So, during that course of discussions we will have more elaborate discussions in terms of entropy. Then moving further, when you talk about aerodynamic objects, that means flow past an external body, a simple thing is a simple shape we can think of is an airfoil, and when you an airfoil is nothing but the two-dimensional cross sections of a finite wing of an aircraft. So, if you talk about an airfoil, this looks of this shape. So, in here we can see that some free stream flow is coming and hitting. So, this is the leading edge of this airfoil, and this point is the trailing edge of the airfoil, and this length is talks about the wing. So, that means it is a extension of wing is L, and this cross section is an airfoil which takes about the shape. So, what we can observe is that we are measuring this distance from this leading edge through this curvature noted by the parameter S. So, if you take an elemental area ds on this wing, what you can say, this elemental area experiences two stress. One is the normal stress, which is nothing but the pressure from this from the outer flow field. Other is the shear stress, which acts the tangentially to the surface. So, basically the net effect and the because of this orientation of the airfoil, the directions of pressure and shear stress is going likely to change. So, as a result, a resultant force will come into this airfoil, and that resultant force is F. And when you decompose this resultant force along the direction of the motion of the free stream, we call this as a drag, and perpendicular to this drag is called as lift. So, basic summary that when an airfoil experiences a pressure difference at its upper and lower surface, it experiences lift and drag. So, these things are quantified through mechanics principles, and they are termed as lift and drag. So, once you do that, one can have the summary that for an elemental area ds, we can have a elemental force, and that elemental force comes in two parts. One is due to pressure, other is due to shear stress, and from this now from this pressure force and the shear force, the net effect that comes in terms of lift, which is lift is nothing but y component of pressure force. Drag force comes as the x component of pressure force plus x component of shear force. Why we do not say that lift is this thing? Because the shear stress, effect of shear stress in the y component is very less as compared to this pressure force. So, that is the reason that the aerodynamic lift mostly comes due to the pressure force. That means, pressure difference between upper and lower surface of the airfoil. So, this is the first part of this video. Now, we will take a break and we will continue the second video of this lecture in a short while. Now, welcome to this lecture again. Now, the part 2 of this lecture deals with the review of thermodynamics. So, in our part 1 lecture, we talked about the fluid mechanics, and in our second part of our lecture, we will be talking about the thermodynamic aspects. Now, we all know that at our UG level, thermodynamics deals with the study of temperatures. Wherever there is a change in the temperature, mostly we deal with this thermodynamics. And why it is important for compressible flow domain? So, normally in the incompressible flow, the fluid mechanics and thermodynamics are treated in two independent manner. But in a compressible flow domain, mainly gases, the essential characteristics is that gas can be compressed to a pressure, any amount of pressure, and during which the temperature is also increased. So, effect of temperature comes in. Now, in a flowing streams, the temperature of gas continuously increases. It gives a combined effect of the flow behavior. That means, in a compressible flow domain, the temperature and pressure effects has to be taken simultaneously. That is one aspect, and in the second aspect is that the kinetic energy associated in a flow field when when we are talking about very high speed flow is quite large, that can alter other flow properties due to strong interaction in the flow. That means, kinetic energy due to this velocity or travelling velocity of the body becomes so significant, it can alter the flow properties. And because of this reason, we treat this thermodynamics and fluid mechanics together in a compressible flow domain. So, what essentially says that at high speeds, when the flow moves over solid bodies, that is an airfoil, or through a duct, that is nozzles or diffuser, or the local velocity or the kinetic energy changes substantially, which is not case for the incompressible flow. The signs of energy, entropy are essential ingredient in understanding the compressible flow, and that we call as a concept of thermodynamics. So, while reviewing these thermodynamic aspects, we say that the characteristics of system is called property, and it depends on the change of the state of the systems. The property can be intensive or extensive, or it can be mass dependent or mass or size dependent. And and in this thermodynamics, what are the major requirement for this course is that we have to have a complete knowledge of a perfect gas and its corresponding equations. We have to know these basic definitions of internal energy and enthalpy, which are derivatives from the first law of thermodynamics. Another important property is in entropy, which is the derivative from the second law of thermodynamics, and the most significant relation, that is called isentropic relations. So, these benchmark analysis is very much required for the for developing theory of gas dynamics. So, you know that perfect gas. So, when you deal with the forces associated or molecular forces, atomic forces, ionic forces associated in a gas, then which is treated as intermolecular force, then if those forces are neglected, then we call this gas as a perfect gas. And in some cases, we call them as real gas, because when this intermolecular force becomes significant. So, in a real gas model, two important parameters drops in. One is gas molecules occupy more volumes with respect to ideal gas of the ideal gas model. That means, size of the molecules in the are neglected in the ideal gas. And there is another parameter drops in, which is the attractive forces between the molecules, and they exert less force on the container in which they are kept, and these forces are neglected for ideal gas. So, what I am trying to say, if for a real gas model, we propose a van der Waals gas equation that talks about the change in the pressure and change in the volume due to intermolecular forces. Whereas, in the real perfect gas model or ideal gas model, we neglect the intermolecular forces. So, this is the vital significant point for a perfect gas and real gas. Now, when you develop these equations, you all know these equations of perfect gas, that is P V is equal to R T, or and this is and then for a chemical reacting systems, we talk, instead of gas constant, we talk analyze that, use that equations on a molar basis. So, that is called as a chemical reacting systems. P V is equal to N R bar T, instead of R we use R bar. N stands as number of moles, whereas in this perfect gas equation we say it is M, it is the which is the mass of the system. So, this is the three category of analysis. One is based on gas constant, second is based on molar analysis, that is for chemical reacting systems, where number of molecules, particles, they are quite significant. And for these chemical reacting systems, they are mostly followed in rarefied gas dynamics. Now in our conventional systems, we will talk about this this gas as a perfect gas equation, and there we use this perfect gas equation as PV is equal to RT. And real gas models, which is the van der Waals equations, in this equation you can say the effect of intermolecular forces is associated with pressure by a term A by V square, and the size of the molecule is gets reduced whilst taking the size of the molecule into picture. Total volume gets reduced by amount minus B. Okay. So, next review point is that we will talk about the internal energy and enthalpy. The internal energy and enthalpy are vital parameters that drops in when we deal with first law of thermodynamics. If you talk about a fixed volume systems, there the changes energy associated with the change in the work and heat transfer is due to internal energy, that is related for a thermally perfect gas it is E, and if it is a flow systems it is recognized as enthalpy. So, internal energy is a function of temperature and specific volume, whereas enthalpy is a function of temperature and pressure. Now, for an calorically perfect gas, we can write E is equal to Cv times T, H is equal to Cp times T. In addition to that, using a gas equations, perfect gas equations, one can write the specific gas constant R, specific heat ratio Cp by Cv, and we also have definitions for specific heat at constant pressure and constant volume in terms of enthalpy change with respect to temperature at constant pressure, which is recognized as Cp, that is equal to gamma R by gamma minus 1, and similarly Cv is equal to R by gamma minus 1. Then we try to review the first law of thermodynamics. So, first law of thermodynamics essentially deals with these equations, that is dq is equal to plus dw is equal to dE, which means for a closed systems the parameter associated with work transfer and heat transfer is related to change in the internal energy. And for a reversible process we can write this equation dw in terms of PdV work, and accordingly we can frame different equations for an adiabatic process, isentropic process, all these things. One more important point to be noted here, that or important significance is that the heat and work which is defined by the first law, they are treated as a path functions. That means they are associated with change of state of the systems, where E is the internal energy, is the property of the system. Then the second law of thermodynamics, that deals with occurrence of a systems in a spontaneous manner, and this parameter talks about the directionality of the process, and the law of entropy says that entropy of the universe always increases. So, based on that, if you define in terms mathematical manner, entropy change is associated with reversible heat transfer, and for any non-reversible process, the entropy is always greater than delta Q by T. And the entropy equation talks about that since entropy is a non-conserved properties, so we can write this as ds is equal to ds by dq by T plus delta S ds irreversible, and the law of entropy says that entropy always increases for an irreversible process. then it is very much essential that when you combine first law and second law, we get two important equations that involves all types of thermodynamic properties. So, in the first they are called as TdS equations. TdS is equal to dE plus PdV and TdS is equal to dH minus VdP. So, if you look at these two equations, all the parameters involved here, they are properties. So, they are true, they can be used for any kind of systems and any kind of processes. Adding to that, we also have expressions for entropy change during a process, and it is associated in terms of temperature and pressure change, and also specific heat and constant pressure and specific heat at constant volume. So, these are the working equations for entropy, and also we have an isentropic relations that talks about relation between pressure, temperature and density. So, why we are using this? Because these equations are benchmark expressions that will be used for all types of gas dynamics flow analysis and while dealing with the thermodynamic viewpoint. So, the next part of my second of our thing is that we are going to solve some numerical problems that are associated for this lecture. So, here we dealt with two important aspects, that is fluid mechanics and thermodynamic aspects. So, the first problem deals with the aerodynamics for a flat plate. So, the problem talks about the fact that how a lift and drag gets generated when there is a flow passed in over a flat plate. So, in our example we say that flow passed an airfoil. Here a simplest airfoil could be a flat plate. The problem statement goes like this: a flat plate with a chord length of 1 meter and infinite span is placed in a Mach 2 flow at an angle of attack of 10 degree. The pressure on the upper surface and lower surface are given, that is 54 kilopascal and 170 kilopascal. The local shear force experienced by the plate is 0.35 kilonewton. So, we need to find out the lift and drag force per unit span. So, the if you want to solve the problems, please recall these expressions, that is aerodynamic force on an airfoil consists of two parts, one is pressure force and other is the shear force. So, I put this as term 1 and term 2. So, and this is a case for a flat plate. So, what we can draw is that we can first draw a flat plate which is inclined at 10 degree in the mainstream flow. So, this is the flat plate. This flat plate has unit span and this is given as 1 meter, and it is placed in a Mach 2 flow. That means, there is some free stream which is hitting onto this, that is which is Mach 2 flow, and it is at an angle of attack 10 degree. That means, the axis of this plate and the free stream directions is 10 degree. Pressure in the upper surface and lower surface are given. So, in the upper surface is experienced by uniform pressure, since it is a flat plate. So, each point on these things will experience same pressure force. Now, in this case it is given as 54 kilopascal. So, similarly, in the lower surface is experienced by force called, which is 170 kilopascal. So, upper surface known, and shear stress experienced, and shear stress is being experienced by two sides, one is upper side as well as lower sides. So, shear stress on the upper sides and also lower sides, we call this is 0.35 kilonewton. So, this is tau, this is P. Now, if you evaluate the term 1 for this case, one can say that 1 is both the upper and lower surface direction of the pressure, they are opposite directions. So, you can say 54 is coming down. So, you say minus 54 and it is for unit span plus 170 into 1. So, this we are evaluating for unit span. So, total pressure force, that is term 1 we get as, and this is this we call as F p is equal to 116 kilonewton. And the then and this pressure force has two parts. Now, if you look at the pressure diagram, it should look like this. This what we see is F p, which is going up and shear force which is going along these directions, that is F s, and then we have the direction of drag which is along the free stream flow, which is d, and the direction of lift which is perpendicular to this. So, it is lift, and this angle is 10 degree, and this angle is 10 degree. Okay. Now, it is a simple mechanics principles. We can find out the pressure force and the shear force F s, that is term 2, that is nothing but it is given 0.35 kilonewton into 1 . This F s and F p has two components for drag and lift. So, one can find out that total drag is equal to dw plus ds. Drag due to wave drag due to pressure, that is nothing but F p sin 10 plus twice into F s cos 10, because shear stress acts on the upper and lower surface. So, we have F s and F p. So, we can calculate this total drag as 20.83 kilonewton, and similarly lift force can be evaluated as lift force due to wave drag or pressure drag and lift force due to shear stress. Of course, this number is very less as compared to this, that we can find out here. So, this is nothing but your F p cos 10 minus F s. Looking at this diagram, we can say that it is F p, there is a negative sign will come into picture because they act in an opposite directions. So, this term is 114.2 plus 0.06. So, what we can see is that this term is very small as compared to this. So, this turns out to be, so it may be minus. So, this turns out to be 114 kilonewton. So, ultimately what has been asked, calculate the lift and drag force per unit span. So, total drag force is 20.83 kilonewton, total lift force is 114 kilonewton. So, the basic underlying principle for this. For a simple flat plate, one can say that ratio of lift to drag is almost 6 times, which means that aerodynamics lift is a very essential factor to survive this body at high altitude. Okay. And the second problems that we are looking at is with respect to review of thermodynamics. The problem statement goes like this: a combustible gases undergoes an isentropic expansion in a rocket nozzle from its initial state of 15 bar and 2500 Kelvin. The gas expands to a supersonic speed through a nozzle through the nozzle to a temperature of 1350 Kelvin. We are given with the molecular weight and specific heat for these combustible gases. So, if we can draw the schematic, normally in the gas dynamics terms, these nozzles are typically supersonic nozzles. So, initial state is 15 bar, that means entry state, the flow enters to the nozzle at 15 bar and temperature is 2500 Kelvin, and it expands to a supersonic flow, that is m is greater than 1 and final temperature. So, we can say P1 is 15 bar, T1 is 2500 Kelvin, T2 it is given as 1350 Kelvin. So, it is a nozzle. So, here to do these problems, what we are required? We are required to find out the pressure at the exit of the nozzle. So, we recall isentropic relation, that is P2 by P1 is equal to T2 by T1 to the power gamma by gamma minus 1. This is the isentropic relations and that we understand from our review of thermodynamics. Then here what is not given is gamma. To find the gamma, what information we have given, that is R is 12 and Cp is 4157 joule per kg Kelvin. So, we can find out Cv as Cp minus R, that turns out to be 34 this molecular weight is 12 and R can be treated as 287 joule per kg Kelvin, that is gas constants. So, this then we can find Cv as 3464 joule per kg Kelvin. Then we can find out gamma, which is Cp by Cv, that is 1.4. Sorry, here R is missing. We have given with molecular weight. So, since it is a combustible gas, so we recall that R is equal to R bar by M. R bar is universal gas constant, that is 8314 joule per kg Kelvin. Molecular weight is 12. So, this turns out to be R is equal to 692.8 kilojoule per kg Kelvin. So, if you see here, then we can say Cp is equal to 415 Cv is equal to 4157 minus 692.8. So, this turned out to be 3464.2 joule per kg Kelvin. So, here So, we can find out then Cp by Cv. We have Cv, Cp, we have Cv, that ratio becomes 1.2. So, we can imagine that for air this gamma value is 1.4, but in this case we are using this combustible gases, and this data gives you that gamma value becomes 1.2. So, now the problem becomes very easy. So, P2 we can find out is equal to P1, which is 15 bar, T2 is 1350 divided by 2500, gamma 1.2 by 0.2. So, this will give you P2 is equal to 0.372 bar. So, the answer is exit pressure at the exit of the nozzle is 0.372 bar. So, with this I conclude for this lecture. Thank you for your attention.